Okay, here's a problem where we're asked to draw the shear force and bending moment diagram for the frame. So we've talked about these. So the first thing I would suggest that we do is go ahead and find the reaction. So I'm going to draw a quick free body diagram of the whole structure and find the reactions. And then the next step would be to take the frame apart at B and C and find those internal forces. And then once we have that information, we can draw the shear force and bending moment diagram. So I'll just use the drawing itself as my quick free body diagram. So I'll have a force AY and AX, and then one here at DY. Also, I'll go ahead and convert the distributed load that's being applied to AB to a concentrated equivalent to help me out. So it's 12 feet tall times 3, so that's 36 kips. And from A, that would be half the distance, or about 6 feet. So let's go ahead and find the reactions. So I'll start by summing moments at A and assuming right-hand rule for my sign convention. So looking at all the forces about A, the concentrated equivalent and this applied force are both creating what? Positive or negative moment? Negative. So I'll have negative 36 kips times a moment arm of 6 feet. And then 15 kips, that moment arm is 4 feet. And then dy, the way I've assumed it, is going to create a positive moment, right? And that has a moment arm of 8 feet. So we should be able to solve for dy. You guys have to help me out with that. I don't know what this is. 34 and a half? Anybody else get that? Great. All right, so let's go ahead and finish up with our reactions. So we'll sum forces in the y direction. So I have AY is acting up. DY is also acting up. And then the only other y force is this 15 kip force, and that's acting down. So I plug DY in here. I should be able to find AY. It looks like it's going to be negative. What is that?
Negative 19 and a half.
Does that make sense to you guys? This is a pretty large force here, and it's attempting to really overturn the frame to basically cause it to rotate about D. So in this case, AY is really holding the structure down. And we've talked about that before in wind loads, tornadoes, hurricanes. A lot of the forces are uplift forces, trying to pick your structure up, and this is a case that's similar to that. And then the last thing I'll do for my reactions is to sum forces in the x direction. In this case, I just have AX to the right, and I also have this big 36 kip force to the right. So AX is, I think I can solve that. That's minus 36, right? Okay, so now we want to start taking the structure apart in this problem at B and at C and find the internal forces. Which free body do you want to use? We can look at, let's talk about B first. So do you want to look at the AB free body diagram or the BC? Or the BCD free body diagram? There's really two ways. When you cut something, you're always going to look at, one side or the other. I don't see a huge advantage going either way. maybe just because we haven't seen it before, I may cut it here at B and look at this part of the structure. That sound okay? Or do you want to look at the left side? It's not really left and right. You guys have a preference?
Do that little corner, PCD.
This side? Okay, so let's look at, so I'm going to cut it at B. And when I do that, we're going to look at this side. I have dy, and what is dy?
34.5.
So I'll just write that in there. 34.5, and this is kips. This was 12 feet tall. I have my 15 kip load, and this is at 4 feet and 4 feet. And then I have the internal stuff. Now, what am I going to assume here? Well, I'm just going to assume at B I have a Y force, an X force, and a moment. Right? 3 things I know, I can write 3 equations. So what equation should I write first? You want to sum moments? What do you want to sum moments about? That is a good choice. So we'll sum moments about B. Why is that a good choice?
Because it knocks out all of it.
Yeah, so BY and BX act through B, so I have to worry about that. So I'll get my moment in terms of the 2 forces that I know. So I'm still assuming right-hand rule. So using right-hand rule, what kind of moment is this? Positive or negative? Negative. So I have the moment at B. 15 kip force creates positive or negative moment? Negative. And it has a moment arm of 4. And then this big 34.5 kip force creates positive or negative? Positive. And that has a moment arm of 8. So you guys will have to help me out. What's the moment at B? It looks like it's going to be positive. What is it?
216.
216. And that'll be kip feet. Anybody else get that? Is that okay?
Yeah, good.
Excellent. All right, now we'll sum forces in the y direction. So I have BY acting up. Got this 15 kip force acting down. And the 34.5 reaction, that's acting up. So I should be able to find BY. BY looks to be negative.
Negative 19.5.
19.5. Anybody else get that? Does it look okay? Cool. Then the last one is X. So I'll sum all my forces in the X direction, make sure I'm in equilibrium. It looks like I have BX and nothing. So it looks like BX has to be 0. Okay? So I've got my internal forces at B. Let's go to internal forces at C. So I'm going to cut it at C. Do you want to work the left side, A, B, C, or the right side, C, D? I think here there's a clear choice. I would say C, D, yeah. So I'm going to try to squeeze that in right here. So I'm going to cut at C, and when I draw the free body diagram, it's going to take me longer to draw it than it is to write it. I'm going to find that I have my reaction at D, which is 34.5 kips, and then internally I have CX CY, and a moment at C. So what do you want to work first? Again, in these problems, it's typical to help you get started is to sum moments at that cut position. So I'll assume right-hand rule is my sign convention, so I'll sum moments at C, make sure they're in equilibrium. What are the moments about C? Well, I have my moment MC and nothing else. So the moment is 0. I'll sum forces in the Y direction. What do I have? I have CY acting up. I have 34.5 kips also acting up. So CY must be negative 34.5. And then last, I'll sum forces in the X direction, assuming right is my positive convention. And all I have is CX, so it must be 0. So there's a lot of statics to get started. Any questions about that?
Why did you assume that the moment about C was that direction? It should be
I just assumed it.
I know it's 0 either way, but
I just chose something. I just did right-hand rule.
right.
When I draw my shear force and bending moment diagrams, then I would be concerned about what direction that is. I may have cheated a little bit in that I looked ahead and saw that the moment was 0, so I really wasn't concerned about it at all. So I'm going to peel this off a little bit and keep these values handy, but let's draw the shear force and bending moment diagram. So I have an extra piece of paper I can draw those on. And I'm going to do the little trick I showed you earlier about rotating the geometry around. So let's draw the shear force and bending moment diagram for section A to B. So what I'm going to do first is I'm going to draw that section A to B. So I'm going to rotate it over so that I now have it kind of in our more traditional form that we've done for beams prior. Now let's go back and I'll put this here so you can see it. What was my reactions at A? Well, in this orientation, when I rotate it, here's my beam, AX is my shear force on the end. And what do we find AX to be? Okay, so that means it's actually to the left, which in this case is up of 36 kips. Right? Now what's the force here at B? Well, again, if I rotate over, that would be the force here at B. Now, we solved for it on this side. So that would be what?
BX.
19.5.
So we found BX here was 19.5 negative, which really means on this body it's to the left. So our body would be to the right, or in this case, down. Right? Is that right?
Yeah. It's 0, right?
Is BX 0?
No.
Oh yeah, BX is 0.
So it is.
Okay, I was looking at B1.
Yeah, I was too, sorry. Yeah, so it's 0. So nothing here. What's the moment at A? What's a pin? That's 0. What's the moment at B? We saw for the moment at B, it was 216. Now, it came out positive in this direction, which is clockwise. So that means on the other body, it's counterclockwise. So it would be like this. So we transferred all the information. Oh, I did leave off that this was 3 kips
I
per
don't
foot.
like that 36 is going up right there.
You don't like that?
No, sir.
Why not?
Right.
What don't you like about it? Let's go back and look at our original diagram. So here it is. So I assumed AX was to the right, and we found AX to be negative. So that means it's to the left. But when I rotate it, that means it's up.
I like it a lot better.
You like it better now? All right. So now that we have this, let's go ahead and draw our diagram and see what we get. So I'll extend my template here, and I'll assume positive X, positive shear. So what is the shear force at A? Positive or negative? That's positive shear, 36. Now remember, our rules say that the change in shear is equal to the area under the load diagram. What's the area in the load diagram over 12 feet? Should be the area of this curve is a rectangle, so that's base times height. 12 times 3 is 36. That's negative, so 36 minus 36 is 0. And that matches that we have no shear force on the right-hand side. Also, we know that the shape of the diagram is equal to the load. And the load in this case is constant, and it's negative. So I know my diagram is a little tiny there. I'm sorry about that. But you can see it's just a triangular shape. So now we'll draw the moment diagram. So there's my positive directions, and my units are in kip feet. What is the moment at A? 0. What is the bending moment at B? Positive 216. We know that the change in moment between any 2 points is the area under the shear diagram. What is the area under the shear diagram? It's a triangle, so it's 1/2 base 12 times height 36. Hopefully that's 216. So that positive area tells us that we do in fact go from 0 to positive 216. That's great. And we also know that the slope of the moment diagram is equal to the shear. So what does our shear start off at? Big. And decreases to 0. So there's our slopes. So if we try to draw something that fits that, we'll get something like that. There's our moment diagram. You like that? Well, I guess I shouldn't say like.
I like it.
Any questions about this particular
I like
procedure?
it color.
All right, so let's draw now the diagram from B to C. So I'll put this right underneath it. So there's BC. I do know that right here in the middle I've got a 15 kip load, and that's 4 feet and 4 feet. Now, let's find our reaction. So if you go back and look at our previous page, here's our reactions at B. So By is the shear force at B, and what do we get for By?
Negative.
So it's actually down, right? 19.5. So I'm going to start here, down 19.5 kips. And then I'm going to go over to C. Okay, when we solved for CY, we did that on section CD, and we found that CY was negative 34.5, which means it's actually down.
But it's rotating.
But on the other body, it's up. So that's 34.5 up. What's the moment at B? It's 216. Now remember, we solved for it here, right? There's By, and we got 216. So it's positive, so that means I have a positive moment of 216 kip feet. What's the moment at C? 0. So now we have our information. We're ready to draw our diagram. So this will begin and end. Something's going to happen in the shear diagram at 15, so I'll add that. So let's do the shear diagram first. So positive X, positive shear. All of our units will be in kips. So what is the shear at A? Is this positive or negative shear? Negative shear. So we're going to start off at negative 19.5. The change in shear is there in the load diagram, which is 0. So there should be no change. And then the shape of the shear diagram is given by the load. The load is 0, so 0 slope. Now, as we go from the left side to the right side and we pass by this 15 kip force, what happens? We drop down 15. So hopefully that'll bring us to 34.5. The change in shear over the last 4 feet is given by the area under the load diagram, which is 0, so it matches what we expect the shear to be here. Also, the slope of the shear diagram is given by the load. The load is 0, so we have 0 slope. So you get this kind of stepped shear diagram. Okay? Now the last one we'll draw will be the moment diagram with units, kips, and feet. Is it still visible? Yeah, it's still visible. So we're going to start off with what's our moment at B? Looks like it's 216. Is that a positive moment or a negative moment? Positive. So we're going to start off at positive 216. The change in moments area of the shear diagram over the first 4 feet. What's the area of the shear diagram? Well, it's rectangle, so it should be base times height. 78. And that's negative, so what's 216 minus 78? What is it?
138.
138. And the shape of this curve is given by the shear. And the shear is constant. So I have a constant slope, and it's negative. Now the change in moment over the last 4 feet is given by the area of the shear diagram, which is this part here, which would be 4 times 34.5. Let's hope that's 138. It is. That brings us to 0. Great. And then the slope is given by the shear. The shear is constant and negative, and it's larger than the previous one, so you can see there's a nice little bend here. So there's our shear diagram. So you can see these problems are not hard, but they do take a lot of time. So in quick summary, look at all the work we had to do just to get started. Do find reactions. We had to cut the structure for this particular problem in 2 spots and do 2 method of sections problems to find another, in this case, 6 unknowns. And then using all that information to construct our shear force and bending
So we
moment.
don't have to draw the third one if we know there's nothing on it, right?
There's nothing there. You don't have to draw it. Yeah. I should mention that, there's nothing going on in CD. If you go back to our original work, we found what? No shear, CX is 0, no load. The moment was 0, no load. So nothing's happening there in terms of shear and moment. However, if we were concerned about axial force, you would notice that this element is being compressed. And we're not drawing axial force diagrams.
Oh.
Okay, any other questions?